It's pretty easy to think of AI, cutting edge AI, is mostly working on flat screens, right, in 2D.
That's the common picture.
But then you think about all the data that's naturally well curved, like Earth's climate or 360-degree photos, even mapping galaxies.
Absolutely. There's a huge amount of it, and that's where the problem lies.
Right, the mismatch. Because our standard AI models, even really powerful ones like transformers, they're fundamentally built for flat Euclidean space.
Exactly. They just aren't designed out of the box to handle the specific geometry, the symmetries you find on a sphere. If you try to force spherical data onto a flat map,
You get distortions, you lose information, especially with that curvature.
precisely, which leads us nicely into the research we're diving into today, attention on the sphere.
Sounds intriguing. What's their main goal here?
Well, their mission really is to take that powerful transformer architecture and make it work natively on spherical data, to make it respect the geometry.
So enabling AI to actually understand the world, or the cosmos, in its actual curved shape, not just a flattened version.
That's the idea. It's about tackling that fundamental challenge.
Okay, so what's the core problem they're hitting head on? With standard transformers, I mean.
The big issue is the attention mechanism itself. Standard attention is what we call permutation equivariant.
Meaning it doesn't inherently get spatial relationships. It just sees a set of points.
Exactly. It usually needs something extra, like positional embeddings, to tell it where things are relative to each other.
And on a sphere, especially if you use a typical map projection, like the rectangular ones we often see.
Right, like an equirectangular projection. That lack of built-in spatial understanding, combined with the projection distortion, particularly near the poles where things get really stretched or squished, leads to significant errors.
So the goal isn't just making it work on a sphere, but making it work in a way that understands the sphere's properties.
Yes, specifically they aim for rotational equivariance. That means if you rotate the sphere, the AI's understanding, its output, rotates consistently with it. It doesn't change arbitrarily.
Which sounds critical for physical accuracy, like in climate science.
Absolutely paramount. For this deep dive, we're looking at their main research paper and some supporting docs, which really lay out the technical side and the experiments they ran.
Great, so let's get into the innovation itself, this spherical attention. What's the big idea theoretically?
The core concept is generalizing attention from that flat Euclidean world to the continuous surface of the sphere.
Okay. How does that work conceptually?
Think about kernel regression. You use a kernel function to measure similarity or correlation between points, right? They're essentially framing attention as a form of kernel regression directly on the sphere. So the model learns to assess relationships based on the actual curved geometry, not some flattened approximation.
Interesting. So it's building that understanding of closeness or relation right onto the sphere itself. But you mentioned respecting symmetries. How do they guarantee that rotational thing, the equivariance?
This is where a really elegant piece of math comes in, the invariant Haar measure on the sphere.
Hair measure? Okay, break that down a bit.
Think of it as the mathematically correct way to measure area or integrate functions over the sphere such that the measurement doesn't change if you rotate the sphere. It's inherently rotationally invariant.
It's like how a square kilometer is a square kilometer no matter where it is on Earth.
Exactly analogous. By using this Haar measure to define their continuous attention formulation, they build that rotational symmetry right into the foundation. It's not an add-on, it's fundamental. This SO3 equivariance is a key theoretical leap.
Okay, that sounds powerful theoretically, but data isn't continuous, it's points on a grid, right? How do they make this practical?
That's the next crucial step. They use numerical quadrature rules.
Quadrature, like numerical integration.
Precisely. These are methods to approximate an integral using a weighted sum of the function's values at specific sample points on the sphere.
So you have your data points, and each gets a weight.
Exactly. And these weights are super important. Why? Because sampling on a sphere often isn't uniform. Think about a simple equiangular grid longitude and latitude lines.
Right, you get way more point bunched up near the poles than at the equator.
Yes, the quadrature weights correct for that. They effectively give less weight to points in densely sampled regions and more weight to points in sparsely sampled regions, ensuring every part of the sphere contributes fairly to the attention calculation.
So it stops the poles from dominating just because there are more sample points there. Makes sense.
And figure 1 in the paper shows this really clearly. You see how this weighted spherical attention avoids the kind of mess you get if you just naively apply attention or use a flat approach.
That visual comparison helps. You also mentioned this positions their method as a neural operator. What's that mean here?
Right. A neural operator basically learns a mapping between function spaces, often infinite dimensional ones.
Okay.
In this context, it means their attention mechanism isn't just learning on one specific grid grid or resolution. It's learning a fundamental operation on the sphere itself. The quadrature rules are then just the way you apply that learned operator to whatever discrete set of points you happen to have.
So it's more flexible. It could work consistently even if you change the resolution of your spherical data.
That's a big advantage, yes. It offers consistency across different ways of digitizing the sphere.
Okay, so that's the core spherical attention. But global attention, where every point looks at every other point that gets computationally expensive fast, right?
Hugely expensive. For high-resolution climate models or detailed 360 images, N-squad complexity is just not feasible.
So they needed a way to scale this.
Which brings us to spherical neighborhood attention. It's their solution for efficiency.
Neighborhood. So limiting the scope of attention.
Exactly. Instead of every point attending to every other point globally, each point only attends to other points within a defined neighborhood around it.
And how do you define a neighborhood on a sphere? It's not just a square grid.
They use the geodesic distance, the shortest path along the curved surface of the sphere. They set a cutoff distance, theta cutoff, and the neighborhood includes all points within that geodesic distance.
Okay, so it's like drawing a circle on the sphere's surface around each point.
Pretty much, yeah. And this drastically reduces the computation. Instead of n squared, the complexity becomes roughly OKN, where k is the average number of points in a neighborhood. Much, much more scalable.
That definitely helps with computation. But does limiting attention locally mean you lose the big advantage of transformers capturing long-range dependencies across the whole sphere?
That's a fair question. It does introduce what's called a locality bias. The model naturally pays more attention to nearby interactions.
Which might actually be good for some things, like weather patterns.
It often is, yes. It's a useful inductive bias. But the really neat part is, even with this localization, they still maintain approximate rotational equivariance.
How? Because it's still built on that continuous formulation.
Exactly. The foundation is still the continuous Hare measure and the quadrature discretization. So they get this computational speed up and the locality bias without totally sacrificing the crucial geometric symmetry. It's a smart trade-off.
Okay, makes sense. So they have these spherical attention building blocks, global and neighborhood. How did they actually build full models like spherical transformers?
They were quite systematic. They took well-known, successful Euclidean models, specifically vision transformer, or VAT, and segformer.
Right, common in computer vision.
And they adapted them. The core idea was find the parts designed for flat grids and replace them with spherical equivalents.
So what got swapped out?
Well, things like the initial patch embeddings or the standard 2D convolutions you find in those models, those were replaced with discrete continuous spherical convolutions, which, again, are designed to respect that SO3 symmetry.
Okay, convolutions handled. What about the attention layers themselves?
That was the most direct swap. The standard Euclidean multi-head attention layers were just replaced with their new spherical attention layers, either the global or the neighborhood version, depending on the model variant they were building.
And things like upsampling for segmentation.
They used spherical bilinear interpolation for that, again ensuring the geometry is handled consistently throughout the network.
One more piece. Standard transformers need positional embeddings because the attention itself is permutation equivariant, right? It doesn't know where the tokens are. How does that work spherically?
Good point. Since the attention mechanism, even their spherical one, doesn't inherently encode absolute position, you still need to provide that information.
So spiritual positional embeddings.
Yes, they use spectral positional embeddings. These are derived from spherical harmonics.
The basis functions for spheres, like sines and cosines, are for lines or circles.
Exactly that analogy. Spherical harmonics provide a natural, complete, and geometrically consistent way to represent functions and thus positions on a sphere. These embeddings give the model the necessary spatial context.
Okay, so they've rebuilt VOT and segformer into spherical versions using these components. How did they test them? What was the validation process?
They picked three really different and important tasks. First, simulating shallow water equations on a rotating sphere.
The Krivit modeling testbed. Very sensitive to geometry.
Extremely. Second, spherical image segmentation using the Stanford 2D 3DS dataset. Think understanding scenes in 360-degree images for robotics or VR.
Right, practical perception.
And third, spherical depth estimation using that same dataset. So figuring out distances in those 360 views. Diverse tasks, all inherently spherical.
And the results. Did the spherical versions actually do better?
Yes, consistently. Across all three tasks, the spherical transformer variants significantly outperformed the standard planar versions that were just applied to flattened projections of the spherical data.
Can you give some specifics like for segmentation?
For segmentation, their spherical segformer got much better IOU intersection over union and overall accuracy scores. Basically, the predicted object masks were much more accurate.
And depth estimation.
Similar story, lower errors in predicting the depth, meaning more accurate 3D understanding from the spherical images.
What about the shallow water equations? That seems like the acid test for geometric accuracy.
Absolutely. And the results there were particularly compelling. Figure 5 in their paper is quite telling. It visually shows how the spherical neighborhood transformer drastically reduces the errors, especially the distortion you typically see near the poles when using a flat Euclidean model.
So it really demonstrates the benefit of handling the geometry correctly for physical simulations.
Definitely. They also compared their spherical segformer against another existing spherical model, sphere U-former, and found their larger version set a new state-of-the-art for that segmentation task.
Wow, okay, so strong validation across the board. Seems like a real win for the spherical approach. But like all research, there must be limitations or next steps, right?
Oh, for sure. They're upfront about that. One practical issue is the speed of their custom CUDA kernels for the spherical neighborhood attention.
The implementation details.
Right. Theoretically, neighborhood attention is faster, ON. This is ON2. But in practice, their current custom code isn't as highly optimized as the standard attention kernels that libraries like PyTorch have spent years perfecting.
So it works, it's conceptually faster, but the raw speed isn't quite there yet compared to heavily optimized standard stuff.
Pretty much. They mentioned they're working on optimizing them things like using reduced precision, maybe leveraging tensor cores on GPUs. And they point out that very fast implementations do exist for neighborhood attention on Euclidean grids, like NATN.
So there's a path forward for optimization, it sounds like.
Hopefully, yes. Another limitation is the need for distributed memory support.
Meaning?
To train really big models on massive data sets, you need to spread the computation across multiple machines, multiple GPUs with their own memory. Their current implementation doesn't easily support that yet, which limits the scale they can tackle right now.
Okay, scalability for training. Anything else?
One interesting point was about the shallow water simulations. While their model was great at predicting the next time step accurately, when they tried to run it forward autoregressively for many steps to get a long-term forecast, it wasn't as stable as they'd hoped. The errors accumulated over time.
So good short-term prediction, but challenges with long-term stability in those simulations.
Exactly. It suggests there's still more work needed specifically on modeling temporal dynamics, how things evolve over longer times using these spherical architectures.
Interesting. So if we boil it down, the huge step forward here is this properly geometric, rotationally equivariant, or approximately so spherical attention.
Yes, that's the core innovation.
And using that to build spherical transformers leads to clear performance gains on tasks where the spherical geometry really matters. It kind of proves you can't just ignore the curve.
It's a very strong demonstration of that principle. Moving beyond flat Earth assumptions, so to speak, in AI for this kind of data provides real benefits. The better results in fluid dynamics, 360 vision, it underscores the value.
It really does make you think, doesn't it? If we can get better at modeling these global systems or understanding immersive environments, what new insights or capabilities does that unlock? More accurate climate forecasts, smarter robots in complex spaces, maybe even new ways of analyzing cosmological data.
The potential impact is definitely broad and exciting.
And for listeners who are maybe developers or researchers themselves, you mentioned they made the code available.
Yes, which is fantastic. The implementation is part of the Torch Harmonics library, so people can actually grab the code, experiment with it, and maybe even build on top of it.
Great. That really helps push the field forward. Well, this has been a fascinating look at bridging the gap between powerful AI, like transformers, and the actual geometry of our world. A really insightful deep dive.
It's definitely a significant step in geometric deep learning, making AI more aware of the shape of the data it's processing. Lots of exciting possibilities ahead.